In this video, we are going to look at section 1.4, polynomial functions and their rates of change. Our learning target is I can identify key characteristics of polynomial functions and their rates of change. So as a review, a polynomial function is any function whose representation is equivalent to the analytical form p of x equals a sub n to x times x to the nth power plus a sub n minus 1 times x to the n minus 1 power, so on and so forth, until you get to a sub 0, where n is any positive integer and a sub I is a real number for each I from 1 to n, and a sub n is non-zero. So, remember, polynomial functions written in standard form, you only have positive exponents, is essentially what that is saying. And our leading term in any polynomial is the term that has the biggest exponent. So that entire first term is called our leading term. And in this case, it's only the first one because our exponents are written in order from biggest to smallest. And then our leading term also tells us our degree, and our degree, remember, is the largest exponent, or n. And your leading coefficient, so remember, coefficient is the number that is in front of your variable, so that would be a sub n. So for example 1, we are going to find the leading coefficient and degree of the following polynomials, and then we're just going to do a rough sketch of what each one looks like. So remember, for our leading coefficient, we want to find the term that has the biggest exponent, which would be this guy right here. So our leading coefficient is 3, and the degree is 4. And when we are thinking about our sketch, we want to think about if our leading coefficient is positive or negative. So in this case, it is positive. And then our degree, we want to think about even versus odd. And in this case, 4 is an even number. And remember, with even functions, both ends go the same direction, like a quadratic, so either both up or both down. And positive means that both sides are going to be going up. If we had a negative leading coefficient, our both ends would go down. So we can sketch a basic sketch. Our left side would go up. Something may happen in the middle here. Right side will also be going up. Then our next polynomial, y equals 12x minus 7x cubed plus 11. We want to look for the term with the largest exponent, which is actually our middle term here, which means our leading coefficient is negative 7. So that is at negative. And our degree is 3, or odd. So negative means instead of that right side going up, our right side is going to go down. And then because it is an odd function, that means the left and right side will go in different directions. And then we can just give some general sketch of what happens in the middle. Then for C, we have g of x equals 4. Here our leading coefficient is 4, which is positive. And our degree, we can technically write x to the 0th power because there are 0 x's, which means our degree is 0. And if we think about the equation g of x equals 4, which is the exact same as y equals 4, that is a horizontal line. Okay, so degrees of 0, your left and right sides just go straight out to the left and right, kind of like the middle part of a Z, just goes straight horizontal. Next, we're going to look at extrema of polynomial functions. And the extrema of a graph are the minimums and maximums of a function. And we have two types of extrema. We have relative, or they can also be called local extrema. And we also have absolute, or global extrema. So with our relative extrema, they have a relative minimum or maximum where it switches from increasing to decreasing or vice versa. And you can also have a relative min or max at an endpoint. So if we look at the graph below and find all of our possible relative mins or maxes, so we want to find our endpoint or anywhere the graph turns. So endpoints and turns are going to be all of our relative mins and maxes. So we can see we start at an endpoint, and then we have a turn at -2, another turn at 0, and a last turn at 3. And because our function keeps going, that relative maximum at 3 would be our last relative extrema. So then going back through, think about which one is a max and min. We have local or relative minimums at x equals -4 and at x equals 0. So we have a relative minimum here and a relative minimum here. And then our other two turning points would be our relative maximums. So we have relative maximums at x equals -2 and x equals 3. Then when we are determining our absolute extrema or the global extrema, the greatest of all of the relative maximums is the absolute maximum. And the smallest of all of our relative minimums is the absolute minimum. But that only happens if our graph stops. So because our graph keeps going down forever, we will not have an absolute minimum. So we're going to put NA for absolute minimum. We do have an absolute maximum, which was our second maximum, and that happened at x equals 3. And the absolute maximum of our function would be the y value, which is 2. So the absolute max or min is your y value, and then you say where that is by naming its x value. So for example 2, we are going to find our local and global extrema and say what's going on. So for example A, we can see that we have a negative quadratic function, and because it keeps going down forever, we will not have an absolute minimum, right? And then we only have one turning point, which happens to be our relative maximum, which is at x equals 1. And because we only have one turning point, we do not have a relative minimum. And then that absolute maximum is the same as our relative maximum at x equals 1. That absolute maximum is at 3. So remember, we always want to find any endpoints or turning points. So looking at example B, finding our endpoints and turning points, we start at an endpoint of -4. We have a turning point at -2, another turning point at 3, and that would be our last one. So our first relative extrema would be a relative maximum at x equals -4. And then our next one at -2, that would be a relative minimum. And then our last turning point would once again be a relative maximum at x equals 3. And once again, because our function decreases without bound, we do not have an absolute minimum, but we will have an absolute maximum, which is the relative max at 3, which gives us an absolute maximum of 2. So I want you guys to try part C. Then some fun facts about polynomials. Between two real zeros of a polynomial, you have to have at least one relative maximum or minimum. So between any x-intercepts, you have to have a relative max or min. And if our polynomial has an even degree, it will have either an absolute maximum or minimum, but not both. If it's an odd degree, you will have neither a max or a min for absolute. Example 3, for time 0 to 3, the number of cars in a parking lot at time t hours can be modeled by the function c of t equals -1.37 t to the 5th plus 4.21 t to the 4th minus 0.357 t squared plus 3. Based on this model, at what time t does the number of cars in the parking lot change from increasing to decreasing? Now, because this is an application problem, when we look at our graphing calculator, we are only going to look at that first quadrant. Remember, in the real world, we do not have negative numbers. So if we look at our graphing calculator and think about how that kind of looks, we can see our function starts off by increasing, and then at this relative maximum, it will start decreasing. So we're going to do our second trace maximum. Do your left bound, right bound to find your point of 2.446, 31.898. And since it is asking for the time that it changes from increasing to decreasing, that would be our x values. So that is 2.446 seconds is when the number of cars changes from increasing to decreasing. Next, we're going to talk about concavity and points of inflection. So recall that a function is concave up on an open interval if the graph looks like a U or a smile. And we're going to shade the part on our graph to the right that is concave up, which would be the left half of this guy. So that is in green. And then our function is concave down if it looks like an upside down U or a frown. Oh, and we're going to do this in blue. So concave down is the right half of our graph. And then where it changes from concave up to concave down, or vice versa, is what we call the inflection point. And a good estimate of the inflection point is the midpoint of the max and min. So if we think about our maximum and minimum, -2 plus 3 divided by 2, and then our y values, we would do -6 plus 4 divided by 2, and that would give us roughly an inflection point of 0.5 and -1, which would be roughly right there. So example 6 is asking us to determine how many points of inflection occur in the graph below. So it wants us to find each point of inflection, right? So if we think about halfway between our max and our min, if we think about, we have a minimum here at -2 and a maximum roughly after -1. Halfway between those would be at -1/2. So that would be our first point of inflection. And then we would have another point of inflection between our next max and minimum, and that would be roughly at 2 is our inflection point, and that would be our last point of inflection. And then we want to think about where the intervals of concavity are. So if we start with the left side of our graph, we can see that is concave up. So it is concave up from -infinity to approximately -1/2, and then it's concave up again from approximately 2 to infinity. and then between those two intervals is where it is concave down. So approximately from -1/2 to 2. So when we are finding points of inflection, they can occur at one of 3 different places. They can occur at a 0 that has a multiplicity of 3, and when this happens, it will look cubic. So where it crosses that x-axis, it'll roughly look like a cubic function at that point of inflection. And then as we discussed, you can also look between your relative max and min and find that midpoint. And then the last way that you can find a possible point of inflection is between a 0 with a multiplicity of 3 and the closest relative max and min. So kind of a combination of 1 and 2. So between a 0 with a multiplicity of 3 and a relative max or min is what part 3 is talking about there. So example 7 is asking us to find all of the points of inflection using one of those 3 methods. So looking at A, thinking about method 1, if we have a 0 with a multiplicity of 3, we can see that actually at 3, that looks a little cubic. Which means we have an inflection point at 3, 0. We do not have multiple relative max or mins, but we can see we do have a relative minimum at our y-intercept. And then halfway between those, our inflection point, so halfway between 0 and 3, and halfway between -3 and 0 as our y values, gives us an inflection point of 1.5, -1.5. So those would be our 2 points of inflection. We have one at that 0 and one roughly right here. And if you guys will try parts B and C, as a hint, part B, you're only going to use the second one. And part C, you will also only use the second one. So you want to find your midpoints of your maxes and your mins.